So here we have the first part of the repair process of our 3-train spring clock. So we're going to concentrate on the hammer today and just dealing with a couple of relatively small quick gains. The first of these issues, and neither of them are major issues, so the clock would probably run perfectly fine without these interventions, is the fact that the hammer lifting piece, or hammer tail as it's sometimes called, is presently rubbing on the face of the pinwheel. So the pinwheel here, with a little brass pin sticking out, lifts the hammer 1 pin for every hour struck. Now these pins are lubricated, and therefore the fact that the hammer lifting piece is touching the wheel, oil can easily get from the pins to the wheel teeth, which is not ideal. And we see the reason for this is, firstly, the hammer lifting piece is actually bent across a little bit, but secondly, there is a little bit too much what we call end shake. Maybe in engineering this would be called end float, so axial movement of the arbors. Now we need some movement on both arbors, but the hammer arbor can really be reduced virtually to nothing. And this will also help with the damping of the action of the hammer arbor, because it's rattling a little bit as it is. So you can see here there is actually a reasonable gap, and we can take up some of that gap with our new bearing. So yeah, the bearing will have two functions. It'll reduce that axial movement of the arbor, moving the lifting piece away from the face of the wheel. You can see here on the wheel the marks that have been left by the lifting piece over quite an amount of time by the look of it. And secondly, it will damp down the action of the hammer so it doesn't rattle as much. We can see, looking along the hammer lifting piece, that it is in fact bent across slightly, so that's the easiest thing to do to begin with, to straighten it. When we look at our plate, we can see the back plate is engraved, so any bushing we do there will be very visible. So I'm going to make the bush as thin walled as possible, which is good practice because you want to minimize the removal of host material. So I take a piece of hard drawn bushing wire that's maybe about 1 millimeter over diameter of the pivot, and I drill the wire out fractionally undersized for our pivot. Once I've done that, I ream or open up the hole, the pivot hole in the plate. I then measure plate thickness, which, as you can see, is about 3¼ millimeters, something like that, and leave the bush a good amount over length. Once the bush is cut or parted off, I flip it round in the lathe and tidy up the end, although we're going to hammer it in, so that's going to get damaged anyway. So as we put the bush in the plate, you can see that that little chamfer that I turned on there just allows it to begin to enter the hole, but it's still oversized, so it's going to need drifting in. So as I said, I've minimized the wall thickness here to reduce the amount of material we have to remove. You can see that it's left proud by about 0.5 millimeter or something. So I'm going to file down the end of that bush, but I don't want to touch the plate with the file. So I'm going to use this masking tape as a kind of pad to protect the inside of the plate. I could use an end cutter, which is a little tool that's supplied with the bushing machine, but I just want to do this very slowly until we effectively get to 0 end shake on the hammer arbor. it will of course wear in time. Once we've done that, and apologies I didn't film this part, I enlarged the pivot hole with a 5-sided cutting broach, clockmaker's cutting broach, which is a reamer, until the pivot just fits in the hole. I then chamfer on the inside and deburr with a little bit of 4/0 steel wool. And there we have our finished bush or bearing. And as you can see, it stands proud from the plate, probably by 1/4 millimetre or something like that, which doesn't seem much, but it is enough, as we'll see in a minute, just to reduce end shake and yeah, keep the hammer lifting piece off the face of the pinwheel, even when we try pushing the two together. So with that first job completed, it's time to turn our attention to the hammer spring and stop. Now you can see in this parked position that the block from which the hammer shank is made from should, in theory, not that there's anything such as should, but be square with the frame, and you can see it's rotated. What I could do is just bend this spring, the hammer spring, into more of an S shape at the top, which would probably do the job, but so much has already been bent in this clock, I really don't want to continue that process. And also the nose of the spring is reasonably short, so it's starting to move down the sort of inclined plane of the hammer block. So what I'm going to do instead is to straighten the stop, which is bent away. That's going to help us in the first place. And then I'm going to soft solder or lead solder in a block of material, of brass in this case, which will fill that gap and bring that boss square with the plate. We can then straighten the hammer shank as well. So I pierce out a bit of brass, oversized, and then clean the surface and what we call tin the material, which is to apply a thin film of soft solder. I do the same for the hammer stop and apply flux and solder the two things together. Clean off the flux, and once the thing has cooled, I can saw off the excess part of brass. Now you might ask why I use brass and not steel here, because obviously originally you had steel on steel, and it's been like that since the day the clock was made, and almost every clock made is the same. But actually, in terms of transparency, reversibility, ease of doing the work, and a bearing surface, steel on brass is going to be absolutely fine. In fact, if you think about it, almost every other bearing in the clock is steel on brass. So I'm pretty happy with this. I haven't removed any host material, so if somebody in the future wants to come along and remove this block, it's just a few minutes work. So we file the block down so it's slightly oversized. I don't file onto the face of the lifting piece because, again, I don't want to remove host material. And then slowly reduce the height of the face until the hammer block becomes square with the frame. I finished by draw filing, that's filing along the length of the work. And this is what we end up with. Just a pretty obviously added piece of material that could be removed in the future. And as you can see, without bending the spring, the material has rotated the hammer block round so it's square with the frame, which means that now the hammer shank is well away from the frame pillar, and using a brass or rawhide hammer might have been better. I can begin to straighten the hammer shank, and the result is that the hammer action is damped down, the lifting piece is away from the face of the wheel, and the hammer block and shank are now square with the edge of the frame, which arguably is an aesthetic improvement. Not that that's my motivation in the first place. So there we are. The first repair is completed for this clock, and we will be back soon with part 3.